So today we want to look again at triple integrals. This is an extension of what we talked about with double integrals. The big idea is that we just want to describe a region, or in this case, a solid, so that multiple integral can understand, so that a double integral or a triple integral can understand. So here we have a solid, and we're going to describe it to an integral by saying what's x between, what's y between, and what's z between. And we're going to start with something familiar. In this case, we're going to start with a sphere of radius 5. I'm going to write a triple integral for a volume. So that means the function that we're setting up is just the integral of 1 dv. So the format we're going for is we're going to take the integral over the solid W of 1 dv, so that we get the volume of the solid W. So this is the format that we want to use. Now, I know we have a formula for the volume of a sphere of radius 5. 4/3 pi times 5 cubed. That's not the point. In fact, knowing that is the point of doing this integral. You see that if this technology, this new thing, will work on something that we already know as a way to check. So let's first take a look at the equation that we have here for a sphere. A sphere with a radius of 5 is going to be x squared plus y squared plus z squared equals 5 squared, like a circle with one more. If we have a 4-dimensional sphere, we just put the fourth one on, plus w squared equals 5. So it's just the squares of the variables equals the square of the radius. We know that we can't write z as a function of x and y, or y as a function of x and z, or x as a function of y and z, because to solve for any one of those variables, we have to take a square root and square roots into these pluses and minuses. But that's useful in this case because we have this sphere above the xy plane, below the xy plane. Left of the xz plane, right of the xz plane. In front of the yz plane, behind the yz plane. So this sphere has a top and a bottom, a left and a right, and a front and a back. And those are all the 6 equations that we could write for 6 ways we can solve for these variables. So I can write this: z is plus or minus the square root of 25 minus x squared minus y squared. Plus is the top, plus the square root is the top, minus the square root is the bottom. We can also solve this for y. We can also solve this for y and write y is plus or minus the square root of 25 minus x squared minus z squared. In this case, we look at positive and negative y. Positive y is going to be on the right side of the xz plane, minus the square root is going to be the left side of the xz plane. So I might say that the plus square root is the right, and the minus square root is the left. The xz plane marks the middle of the y-axis. And we can also do this for x. Once again, we have plus or minus the square root of 25 minus y squared minus z squared. In this case, the plus is the front and the minus square root is the back. Oh, not the bottom. And so this sphere is going to be the solid W over which we'll integrate. Let's set up a triple integral. We're going to say what's x between, what's y between, and what's z between. So when we set up a triple integral, we got to decide what order we're going to do things. And I'm just going to follow the pattern that I did last time and put z first, and then dy, and then dx. So this last one is going to be the x equals, and that will have to be constants. The middle one will be y equals. Those endpoints will have to be only functions of x. And then the first one will be z equals. Now, if we have a sphere of radius 5, that means all these endpoints are at 5. So if I look at the x's, the lowest x value is here at -5, and the largest x value is up here at x equals 5. So we'll integrate from -5 to 5. Now, for each of these x values, I've got to look at what y value we're going to be between. For each of these x values, we've got to get all the y values in between. And we got to get all the z values. What is z between? So let's actually, since we just talked about it, write down the z values. So I want a triple integral for the entire sphere. So I want the z's start at the bottom of the sphere and go to the top. So the lowest z value is z at the bottom. And the largest z value is up here, where z is at the top. At these 2 points that I picked to label for whatever reason, I picked where z is -5 and z is equal to 5. But z is not always equal to 5 or -5. So part way up, depending on the values of x and y, we have the top and the bottom. So let's integrate from the bottom to the top. So we'll integrate from negative square root of 25 minus x squared minus y squared. Z equals -5 to z equals 5 would give me two planes that I'm between, but I'm not between two planes. The bottom plane is the bottom part of the circle. The top plane is the top part of the circle. So I don't want planes z equals 5 and -5. I want circles or spheres, hemispheres. So I'm going from the bottom hemisphere to the top hemisphere. Any questions? So we got to get those ones in the middle. We got to think about what's going we got to go from left to right. We're going to have to go from left to right. If we look at the top view of what's going on, if we look at the top view, from the top, our contour diagram looks like a bunch of circles. So I'm going to look at this from the top. And here's where I've got x labeled at -5. And down here, I've got x equals 5. Now we're just looking at all these circles. So I just need to go left to right on this circle, x squared plus y squared equals 5 squared. So the left but not the left and right hemispheres. We're just dealing with the circle. So on the left, we'll start with the negative square roots, and we'll go to the right, the positive square root. Top, bottom, or bottom to top, left to right, back to front. Let's take care of at least the first step in this integral. Take care of at least the first step. If we integrate this integral dz, the integral of 1 dz is z. So I'll have the integral from -5 to 5, then the integral from the negative square root to positive square root. The integral of 1 is z, and I evaluate that from the negative square root of 25 minus x squared minus y squared to positive square root of 25 minus x squared minus y squared. That's the dz integral. I still have the dy integral, and the dx integral. X is still going from -5 to 5, and y is still going to go from the negative square root to the positive square root. So now I calculate this definite integral. We do the plus square root minus the negative square root. So we get 2 copies of that square root. And that's where we'll run into the problem. Now, oh man, integrating the square root of 25 minus x squared minus y squared. That sounds awful. Z evaluated from the top to the bottom, or from the bottom to the top, be a plus square root 20 square root minus a negative square root, minus because of the definite integral. So square root plus a square root, we get 2 square roots. Oh, wait, that's not correct. Now let's pause here for a minute and take a look at this double integral. We got the double integral from -5 to 5. The integral from -5 to 5, and then the integral from negative root 25 minus x squared to positive root 25 minus x squared of this function. 2 square roots of 25 minus x squared minus y squared dy dx. So what we're doing is calculating the height above all the points x, y, xy inside the circle. Notice that that region that we're describing in this double integral is the region we have in the circle. And the height above each point in that circle is given by the sphere. And since we want the top and the bottom of the sphere, that's why we double the height. So notice that this region in the double integral this region R is the circle of radius 5. And we did the left and right. That's how we would describe the double integral to for integrating over that circle. If the height above the xy plane is given by a sphere, the height at any point is going to be the square root of 25 minus x squared minus y squared. So the height above the xy plane is given by the sphere. That's the top part of the sphere. And the 2 is because I want the top and the bottom half of the sphere. So after the first step of our triple integral, we get to our double integral. A double integral that's describing the same volume. We're not integrating the function 1 anymore because now we have an expression for the height. And we're saying integrate the height given by this sphere above all the points inside this circle. The integral, when we integrate any integral, if we integrate 1, will give us the size of the interval, region, or volume over which we're integrating. So the integral of from a to b of 1 gives us the length of the interval. The integral over a region R of 1 dA will give us the area of the region R for double integrals. And for triple integrals, the integral over solid W of 1 dV will tell us the volume of the solid. So integrating 1 gives you the size of your input. That tells you the size of the input set. That's why, since this was specifically a triple integral for the volume of a sphere of radius 5, we integrated the function 1 dV to get the volume of W. Now, if this in this double integral, if we replace this height with 1, that would give us the area of the circle. But I want the volume of a sphere, so I'm giving it the height of plus and minus the square root of 25 minus x squared minus y. Okay. That's everything, okay? One of the things that you're going to want to do when you review this setup is to go back and try to match up the things that you see in the triple integral and the double integral with the things that you see in the diagram of the sphere. Notice that I specifically left a lot of the details out of my drawing, partially because I wouldn't be able to successfully draw it so that it would actually help things. It would just make things worse and take a lot of time for me to draw these bad drawings. So I rationalize that by saying we have to start seeing the sphere, the top half, the bottom, the left and the right, the front and back. We have to start seeing that in the integral. We have to start seeing the shape in the equation. That'd be like in the Matrix, where they just look at the screen with all the symbols rolling down, and they see what those symbols represent. It's important to see this when z is plus and minus the square root of 25 minus x squared minus y squared. It's important that we see that as the top and bottom parts of a sphere. With y equals the left and right hemispheres. X equals the front and back hemisphere. That way, if we have something bigger that we can't draw a picture of, like a four-dimensional sphere, x squared plus y squared plus z squared plus w squared equals 5 squared, we just need to come up with a new pair of words. Top, bottom, left, right, front, back. We've used up 3. We need something else. Maybe like inside, outside. Now, that's not good. Let me use the time analogy, before and after, with a plus and minus, or the minus and plus. Any questions? Is everybody okay? I really look so happy to be back after our 4-day weekend. So I want you to see the triple integral and why it works, and I want you to see the double integral that we just integrated our way into, why that works. Now, doing this integral, the integral of square root of 25 minus x squared minus y squared, that would be an interesting exercise in and of itself, but messier than we want to get into now because we're trying to set up triple integral. Here's where we know this is going. So this is going to be a messy integral. So that integral may be a bit messy, but we know where it's headed. The last step is going to be an integral from -5 to 5 of some kind of area to turn into a volume. I spelled area wrong. Whatever else happens, when we integrate that function, 2 square roots of 25 minus x squared minus y squared, after we plug in the y's go from negative square root of 25 minus x squared to plus square root of 25 minus x squared. We should get a function of x that will tell us the area of the circle from -5 to 5. So if we picture what this integral is going to look like, whatever that function is going to look like, we're going to be looking at a circle from -5 all the way up to 5. You just have to think about what those circular slices are going to look like. So for a particular x value, what is that circle going to look like? So for a particular x value, But now we're back in single variable calculus. We're trying to find the volume of the sphere, and we're going to look at this sphere as a stack of circles. We're going to imagine the sphere as a stack of circles. A sphere is just a stack of circles. So if we look at this, if we take this sphere and turn it and look at it from the side, we can see that stack of circles. There's the delta x that becomes the dx. And the radius of the circle goes from the x-axis out to the sphere. To get the area of that slice, we're just doing an old problem from top 2. So let's fill in our details. The height is going to be the delta variable, the part that's getting thinner to make our stack more accurate. Make our circles thinner, our cylinders thinner until they become circles. That's our delta variable. I just have to write r in terms of x. So x is going to be the distance from the origin, so the horizontal distance from the origin to the slice. And then from there, I can get a right triangle with a hypotenuse of 5. That'll give me a relationship between x and r. That'll tell me what the radius is in terms of the x coordinate. So this tells me that x squared plus r squared this tells us that x squared plus r squared is 5 squared. And so that says that r is the square root of 25 minus x squared. So the area of the slice is going to be pi times the square root 25 minus x squared times the delta variable, delta x. That's a circle of radius 0 at -5. It's a circle of radius 5 when x is equal to 0. And when x is equal to 5, it's a circle of radius drop back down to 0. And our total area will be integrating from -5 to 5. We're not calculating the volume area of the slice, we're calculating the volume. I'm going to factor, oh, I'm just going to leave that. All we'd have to do now we can see what the answer is to our previous problem. Our previous problem would be to integrate the square root of 25 minus x squared minus y squared. But at least at this point, we know what the answer is going to be. So the integral from -√25 minus x squared to positive root 25 minus x squared is really going to be pi times 25 minus x squared dx. And at this point, we would want to those are the parts that we haven't filled in. We could take this v total and make sure that it gives us 4/3 pi r squared. Question? Notice that I skipped over the two parts of the problem that are actual calculus. When it actually came time to do the integral, I punched out. I go, nope. Because that's not the point. It's not about finding integral. If in your future career as a fill in the blank, I don't know, you're working on the mission to Mars, you're trying to build a habitat on the moon or something like that. If you're about to do an integral by hand, you're about to get fired. The boss is not going to walk in and say, oh, hey, what are you working on there? Well, I'm going to use trigonometric substitution to do this integral. And your boss is going to say, dude, you have access to millions of dollars of computing power, and you're going to try to run this on a piece of paper. And you're like, oh, no. I got a rocket book. It's actually a piece of plastic. It's going to be like, I'll get out. You know what I mean? It's not about finding the integral. It's about setting things up and understanding the process. So an integral represents a way to think about things. It has to represent how you think about things and how you can describe the world around you. It's not about finding integral. That's always beside the point. That's just a good way to check to make sure that things are going to work out. Make sure that if you integrate this, it works out to 4/3 pi times 5 cubed, like we expected to. Make sense? I can see where the 5 cubed is going to show up. That x squared is going to get to become a 5 cubed. 1/3 x cubed. So I can see where the 1/3 is coming from. I can see where the 5 is going to come from. I'm not sure about that 4. Figure that out. Any questions? This is how we want to view things. All this stuff has to be connected. And that's the point of today. Building a triple integral, just an extension of what's x between, what's y between, what's z between. And when we start following those steps, we take the triple integral down to a double integral, or the first stop after the triple integral is a double integral, which is going to be the integral of some height above or over an area. Then we're going to integrate that again and come up with a single integral, which is going to be the integral of some area over some width or height or length. I can't remember which one's in. So the triple integral, dV is providing the volume. That's your meter cubed. In the double integral, the dA is the area and the function is the height. And in the single integral, the dx is the height and the function is the area. And one just leads to another. There's a lot to do, especially on a Tuesday after a 4-day weekend. So think about it some more. And then make sure you are properly impressed with how well this all fits together. At this point, we could be like, oh, whoa, that's cool. But everybody's like, for the most part, it's like, oh, wait, what are you talking about? Spend some time and you'll see it. That's going to do it for today. I will see you all on tomorrow. We'll think about this some more. Everybody have a good day. Thanks for playing.